Hello, welcome to my first YouTube video. Today I'm going to be building a Motorise Pro version 2, one each for my main telescope and guide telescope. We'll start with a short intro on the features of Motorise Pro 2, and then we'll go into starting the project box electronics build, and then at the end of this video there'll be a maths section, which if you have the equipment stated in the PDF file and are using the recommended motors etc, you can skip the math section. The reason I've included it is because I've been using motors and 3D printed reduction gearboxes that I had to hand rather than buying more motors that were recommended in the PDF. So I hope you enjoy the part 1 of this video. It's going to be 3 parts, so you can skip to wherever you need to find the information. Thank you and enjoy. Hello, welcome to Motorise Pro 2, my first video. Motorise Pro 2 is an electronic telescope focuser primarily for astrophotography, but it's also a focusing remotely without having to touch the scope and avoid camera shake. All the source files can be found at sourceforge.net. Leave the link in the description. For the basic focuser down mode, you'll require the Gerber files if you're going to use a PCB manufacturer, ASCOM drivers, Windows app to post the build config, Arduino firmware, and there is a spreadsheet available for performing the calculations, but I will also show how to do those manually. It's quite a complex piece of kit, to be fair, this one. The hardware options, there are several options on the Focuser Pro, which include push button control, LED or LCD display, temperature probe, a programming switch to aid programming without removing the PCB from the box, performing updates etc, and LEDs. It can be made with PCBs or stripboard. There are stripboard how-tos in the PDF file. My preference was to use PCBs. I ordered 5 from JLC PCB. So for my focus, I've opted to use the focusing and LEDs, power LED, a switch for master switch. The PCB is a revision 12 PCB, I think, yes, revision 12. Bear in mind the PDF file mostly covers revision 11 boards, so some of the items and traces might look different to what you receive, but I have built 2 boards already, one for the main scope, one for the guide scope. They're all ready to program up and go. I won't go into how to solder and build focusers etc. I'm thinking if you've got this far into the project you probably already know that. And there are also plenty of soldering tutorials around on YouTube. So the PCB itself is very tightly packed. I was planning on using the JST connectors for connecting items to the board and the box. So basically when you put that in the box you can go to your switches and LEDs and such like using these JST fly leads. But obviously there wasn't much room on the board to do that, so I have opted for just normal straight pin headers, which the JSTs will fit anyway, so there's no problem there. The motor I'm going to be using is a standard NEMA 17 model, and you'll see when we perform the calculations later I'm having to use a rotary gearbox and the belt drive pulleys to change the step size to make it work. You can buy motors with gearboxes in there, and the PDF will describe best motors to use in given situations, but I'm using stuff I've got to hand, and so I'm just building my own gearboxes etc. In fact, the noise in the background is a gearbox for the other scope, currently printing off. On the main scope I've got aluminium pulley belt wheels, just because I had them to hand basically for the guide scope. I'll be attempting to print some gears rather than buy. We'll see how we get on with that. Printed my own enclosure. There's plenty of enclosure files on Figureverse. So basically when I install, possibly using some adhesive standoffs to place the boarding. This enclosure includes things for the voltage regulator, because these 7805s can get pretty hot. I mean, on a plus note, it will help keep the dew at bay on the telescope. So basically, the reason for the pin headers, for example, that's the switch, so I'll just hook that into the switch pin header and then close it up. I've got 3 LEDs, focus in, focus out and power. There'll be a motor connection to the bottom of the box and the power connection. So obviously the advantage of 3D printing, you can modify the file to put the holes in where you so see fit. So I've got some bits and pieces around. I might have to order a few more as the project goes on. So now I'm ready to build first board. Once we've got this built, we'll go over and install the Windows application and the ASCOM drivers. There are 2 ASCOM drivers available, because for when you use 2. Obviously I'm using the guide scope and the main scope, so I need 2 drivers. There's ASCOM 1 and ASCOM. My Focuser Pro 1 and my Focuser Pro 2. So I'm going to drop that in there. I'm not going to permanently fix anything on here, because I'm going to have to shorten some of these wires up. So let me get my other blank PCB so I can see where I've got to plug them in. So the switch goes to J12, which is this one up here. So the switch, that one goes to there. Red LED goes to that one goes to there. Do you know what? You see what I mean by anything's very tight, packed on this PCB. That diode is almost stopping that going on. So what's next? The blue LED is this one. And the green LED is that one. Oh, I'm going to get my plushes right way around as well. So red is plus, so I'm going to put it that way. Oh, missed it. There you go. Just make sure I've got that right way around, so the plus for the power. Oh no, that's okay. So the red LED plus is away from me, that's correct. So I need to get the power connected before I put these on the case. So the power, so the one is that one. Move the red away from me. Yeah. They are, you do have to make sure you get plus and minuses the correct way round. They are marked on the PCB. And then the motor connection. This is only wired up one way, so you can't go wrong. One note about motors: don't rely on the colour codes. You've got two poles. Two wires for each pole. You need to figure out which two wires are for one pole and which two are for another. They're not all. Unfortunately, the colour scheme isn't universal. So I can give you an example. So we've got red, blue, green and black. Red, blue, green and black, so you've got the same colours but they're not necessarily in the same areas. You'll find that out if your motor's running rough. I believe there's one way to check using the multimeter. If I find that out, I'll drop it in the video. So that's all connected up. Just so when we, at the extremes as well, controllers travel, we don't go. And it can buffers and do some damage. You have to excuse the wire. So that's my power cables from my power supply. Let's get them round on first. Make sure it's switched off. Oh, something just happened. Oh, blue light, come on. Have I put the wrong lamp on? Put the wrong lamp on now. Yep, put the blue lamp instead of the red lamp. That doesn't matter, like. Switch, forgot the switch. Red lamp. Positive, let's do that way. Okay, so we should have a red lamp on now. Just shows us we're plugged in. Ready for the switch. There you go, something just happened. Yeah, motor's energizer. It doesn't sound like it's good on the mouse, but can I feel it clicking? Okay. Okay, time for some maths. Now on your telescope focuser, before I start, the PDF file does give you some preset examples. You might find what you need in there, but if you don't, this is what you need to do. You need to do a bit of maths. So, first thing we need to know is the steps, number of steps per revolution of your stepper motor. My stepper motor in the spec sheet, some spec sheets will tell you the steps per rev, some tell you the step angle. Mine tells you the step angle, which is 1.8 degrees. So you need the formula. I've got some formulas over here. So your step angle 360 divided by your step angle. So 360 divided by 1.8. Let's work that out. So we're on 200 steps per revolution. The next thing we need to know is something called, the focal length of your telescopes. So to find that out, the formula is the focal ratio, which is what you need to know, not the focal length. Focal ratio is equal to focal length times your diameter. So for the 130 PDS, there's T80, which is the scopes I'm making the focusers for. So you've got 650 divided by 130 and 400 divided by 80. F5. Next one, F5. For both scopes, F5s. Let's just circle these around so I know which ones they are. Right, so next, we need to know the CFZ, which is critical focus zone of each scope. So let's say this is your full focus travel. There will be an area within that focus travel where everything's sharply focused. To find that out, the formula is focal ratio times the focal ratio times 2.2. So for both of our scopes, because they're F5, you're looking at 5 times 2.2. So 5 times 5 is 25, so I'll just go straight to that. 55. So our critical focus zone is 55. Next thing we need to know is the step size. So that is what each step, how far each step of the motor will move the focuser. The formula for that is quite large, well, quite a complex one. So you need to know what your one turn of your focus wheel, how far that moves the focus tube, times 1000 divided by your steps per rev. Now my ST80 is 23 mil per revolution. The 130 PDS is 12 mil per revolution. So for the 130, step size is equal to 12 times 1000 divided by steps per rev, which is 200. Sorry, 60 microns. So we've got 60 microns for the 130. For the ST80, it is 23 times 1000 over 200. 115. So basically that means one step of the motor will move my focus tube 60 microns on the 130 and 115 microns on the ST80. Now this is the critical one. This will work out what how many steps in the CFZ you will have. Ideally, according to the PDF, you need around 10 steps, or get as close to 10 steps as you can within that zone. You'll achieve focus quite easily. So the formula, the steps in the CFZ is equal to CFZ divided by, sorry, all the formulas are there, CFZ divided by your step size. So for the 130 it is CFZ is equal to, well, both CFZs are 55. was about focal ratio of f5s, so about 55, so we'll put that in. Over 60 for 130 and 115 for the STI tank. So that's how we go with these 0.916. .478. Now, as you can see, we need to be near 10, and we've got 0.916 for the 130. So that basically means we're going to have one step within that zone. So one step and then we're back out of the zone, so that's obviously not ideal. And the same, we've got half a step. So I mean, we could even bounce completely over the zone with that one. So what do we need to do? We need to get some pulleys and gearboxes. So on the 130 I have printed a 4:1 ratio gearbox, rotary gearbox, to step it down, step the motor down. So what that will have the effect of doing is increasing this by 4 times. So we'll go from 200 to 800. And then I've got, so let's just do it over here. So 200 times 4 is 800. Then 800, I'm going to do a 2:1 ratio again with pulleys. I'll increase it from, so it'll be 800 times, it's actually 2.1. That will give us 1680 steps. So that's reducing our output to 6,000. What did I say? 1,680 steps. Sorry. So if we redo that calculation with 1,680, 7.14 steps, so 7.14 microns. So what I'll do is just so you can read it all afterwards. I'll leave that as 200. Put 168 out in brackets and 7.14 in brackets for that. So this then becomes in brackets 7.14, 7.7 steps. Within CFZ, which will suffice. For the ST80 we need to do something similar, but we need to do it probably twice as much. So what I'm going to do with that is got this, the 3D printed reduction gearbox is modular, so you can lay a 4:1 onto a 4:1 onto a 4:1, etc. So it's times 4, that gives us 800, and it's 800 times another 4, it's 2 4:1s. They compound, they don't add, they multiply. So 4 800s is 1600, 3,200. So let's do that one. I've got to move that out. Oops. 200. Let's do that calculation again. 7.18. So we've got a similar sort of answer there now. Look. So we've got 7.18. So if we now put 7.18 there instead of 55, so it's 55. It's 7.66 steps. Steps. Moving. See what I said. So I think that's pretty close enough to the 10 we need. So if you do these on paper or manually, you need to keep these recorded so you can punch them into the setup software later on. So to keep a note of the answers. One final thing we need is the max steps of your scope. So to work that out is the steps per revolution times the number of turns to go from full in to full out minus half, to give you a bit of space so you don't run out of travel. So steps per rev for 130 it's 1680, sorry, 16, and steps per rev for ST80 is 3200. Remember that's where the gearbox is on. Times number of turns minus half. So the 130 number of turns is, from memory, from 130 is 3.5 turns. Minus half 3 turns. So we got 3 turns on that. The ST80 was 2.5 turns, so we'll go 2 turns on that. Equals 5040. $6,400. So you'll key that into the ASCOM driver software. All of this gets put into the ASCOM driver software, not the firmware for the Arduino board. So do keep your workings out because you'll need them to enter the data in the ASCOM driver software. And that's that. Big complex now. If you're lucky enough to have a given setup in the PDF file, there are several, then away you go. But if you haven't, you need to do this. Okay, we'll conclude that part 1 for now, especially if you've done the math section. See you next time for part 2.